Welcome to science class. Today we are going to learn about ocean currents. Ocean water is not static, and I don't mean waves. Large masses of water circulate around the globe. Ocean current maps usually look like this. This gives the big picture, but it's not very precise. Here is a highly detailed ocean current map. You can see that rather than large, continuous ribbons of moving water, a single current is really made of a huge number of smaller currents that, overall, flow in a particular direction. These types of currents move laterally, but there are also vertical ocean currents. Currents are highly influential parts of Earth. They shape the climate as well as the biosphere in important ways. Let's get started. We will begin with currents that circulate water horizontally. Known as surface currents, these develop because of friction between the wind and the water surface. To understand surface currents, we have to understand wind. We will cover wind in more detail in the future, but here's a sneak peek. Earth is a sphere, and that shape causes a disproportionate amount of heating. At the equator, there's a lot of heating, while as you move towards the poles, the same amount of sunlight gets spread over a larger area, so the heating is more diffuse. There is less heating. Air is warmed and rises at the equator. Then at around 30 degrees latitude, it cools and sinks. This then causes the air to circulate back towards the equator. Some of that air, however, pushes towards the poles, and at around 60 degrees latitude, it rises, circulates back to where it came from, then falls again. These huge pockets of rising and falling air are called Hadley cells. These represent the movement of air north and south, but it's not as simple as that. Earth is a rotating sphere. This means that the equator, Earth's widest point, is also its fastest moving point. At the equator, Earth rotates 40,000 kilometers every 24 hours. But at 45 degrees latitude, the circumference of Earth is only about 28,000 kilometers. So Earth rotates a shorter distance in the same amount of time. Hence, it is moving slower. This causes air that moves north or south to be deflected. As the air travels back towards the equator, it is traveling to faster rotating regions, but it keeps its original speed. Similarly, as air moves away from the equator, it moves into slower rotating regions, but it keeps its original speed. This causes the air currents to be deflected, and this is known as the Coriolis effect. Because of the Coriolis effect, air currents, and therefore ocean currents, circulate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. If Earth rotated the other direction, it would be the opposite. I know this is confusing, so let's try to visualize it this way. Imagine you are in a plane at the equator. You point the plane directly north and begin flying. Where do you end up? Well, north isn't your only motion. You're on a planet, and the planet spins towards the east. So your plane is really moving northeast. You carry that easterly momentum with you as you fly north, where Earth spins more slowly. So you end up flying more and more sharply to the east as you move north. This is precisely where the clockwise motion comes from. If we were to do the opposite and fly towards the equator from the north, all these things would be reversed, and you would be deflected towards the west, as the east-moving Earth that is gradually spinning faster below you goes by. So, bottom line is, surface currents happen because of the wind and Earth's rotation. Collectively, these small regions of wind around the world add up to create massive gyres, which are big circulating masses of water. There are 5 main gyres in the North and South Pacific, North and South Atlantic, and there's one in the Indian Ocean. And these gyres have massive effects on the planet. Take a look at these 2 climate graphs. One is for St. John's in Newfoundland, and the other is for Nantes in France. The temperatures in the summer are around 7 degrees Fahrenheit warmer in Nantes, and in the winter, they are well over 10 degrees warmer. Nantes does not have any months where the average temperature is below freezing, while in St. John's, 4 months out of the year, the average temperature is below freezing. This is significant because these 2 cities are at the same latitude. They are both equally far from the equator. So why are they so different in temperature? Both cities are on the Atlantic coast, but St. John's is on the wrong side of the Atlantic. Because Earth spins west to east, the ocean currents in the northern hemisphere rotate clockwise. This causes warm water to circulate from the Gulf towards Europe. Europe is way farther north than you probably think it is. The southernmost point in Europe is at about the same latitude as Nashville, Tennessee. The entirety of the United Kingdom is farther north than the whole United States apart from Alaska. The Gulf Stream current delivers warm waters to Europe, and this warms the air, making the climate much warmer than the equivalent location on the opposite side of the Atlantic. Let's compare the east and west coasts of the United States. In South Carolina, the ocean temperatures are several degrees warmer on average than they are in Los Angeles, which is at approximately the same latitude. This is because on the west coast, the ocean currents are circulating down from higher latitudes where the water is colder. This is why hurricanes never occur on the west coast. The water is too cold and the currents circulate in the wrong direction for them to form. Again, if Earth rotated the other direction, this would be reversed, and California would get hurricanes every year, and the East Coast never would. Cold water currents help to moderate the climate. Wilmington, North Carolina, and Los Angeles are at approximately the same latitude. While the winter months are noticeably warmer in LA, the summer months are almost identical in average temperature. Cold water currents don't make winters colder, but they make summers cooler. Similarly, warm water currents don't make summers hotter, they mostly just keep winter months warmer. Surface currents also cause water to move vertically. As the wind blows the water's surface, it draws the water down slightly. This forces deeper water to rise up to replace it. This vertical movement of water is called upwelling. Oceans get their sediment from eroded sediments on land, which settle to the bottom. Upwelling forces these sediments to mix in the water, which in turn makes their dissolved nutrients available to photosynthetic organisms. Upwelling plays a crucial role in what's called the primary productivity of the coasts, which is the rate at which photosynthesizers, which we call producers, grow. This, in turn, supports all other marine ecosystems and food chains. Using satellite technology, we can map the density of chlorophyll in the oceans, and what we see is it is highly concentrated just off the coasts, and that brings us into vertical currents. Truthfully, these aren't really currents, but water does circulate vertically in the oceans as well. Apart from upwelling, the only other way in which water moves vertically is due to differences in density. When it comes to ocean water, the only way to change its density is to change its salinity or change its temperature. We will go over salinity first. There are two ways to increase the salinity of seawater: through evaporation or the formation of ice. When water evaporates, dissolved substances do not evaporate with it. Because of the massive size of the oceans and the circulation of ocean water, and the fact that most of the water that evaporates falls back into the oceans as rain or runoff, evaporation does not play a significant role in changing the density of seawater in the tropics, where evaporation is highest. Ocean water is more dense at the poles. The fact that the water is warmer in the tropics also negates the evaporation process, because water is less dense when it is warm. But in the Mediterranean, it is a different story. The Mediterranean Sea is connected to the Atlantic through the very narrow Strait of Gibraltar. The climate and geography of the Mediterranean makes it significantly more dense than the Atlantic, due to high amounts of evaporation, which is not offset by precipitation or runoff from rivers. The salinity of the Mediterranean is around 38 parts per million compared to 35 parts per million in the Atlantic. So the water of the Mediterranean flows into the Atlantic underneath the incoming current of water from the Atlantic. Ice formation and cold temperatures, which also increase ocean water density, go hand in hand. When ice forms, salts do not get trapped in the ice. The water around the poles is the most dense due to the sea ice that forms, leaving the salt behind, and the fact that the water is very cold. Over the course of many thousands of years, water can circulate from the poles downward and migrate towards the tropics, where it warms and rises again. Sea ice is seasonal, so the density of the water around the poles changes much more than it does in the tropics, as the water is diluted by the melting of all that fresh water in the form of ice. And those are water currents. Next time, we are going to discuss how the tides work. Thanks for watching.